Okay, morning, everyone. I am Rebecca Wright, Chair of Computer Science at Barnard, and we're very happy to have for our computer science seminar today our speaker, Kavya Ravichandran. Kavya is a PhD candidate at the Toyota Technological Institute at Chicago, advised by Avram Blum. She works on machine learning theory and algorithmic decision making, and is recently focusing on the work she's talking to us today about on improving multi-armed bandits and pessimism traps. Before she was at TTIC, she completed her master's and bachelor's degrees at MIT, and she has been recognized as a rising star in things including IEOR and another bunch of initials that I that I can't quite parse here. And also has been involved a lot in mentoring of math and computer science young students, including through the Girls Who Code clubs in Chicago. And with that, I will hand off to Kavya.
Thanks so much for the introduction. Hi, everyone. Thanks for coming to my talk. I'm excited today to share with you some of my recent work on sequential and social decision making, and I'll get into what I mean by that and all these other topics. So in the last couple of years, I've been working on a broad range of problems in machine learning theory and decision making. And so some of the themes have included extracting structure from data, the role that optimization plays in machine learning, and also decision making. But before I jump into that, I want to tell you a little bit more about myself, who I am, how I view myself as an academic. So as an academic, I view myself as a steward for knowledge, and I really value the chance to create knowledge by doing research, teach it to students in the college and university setting, and also disseminate it as widely as possible to the broader community. And so to that end, in the last many years, I've been involved in a number of different activities. So one is teaching for introduction to machine learning, information theory. I've done a lot of assignment development associated with those courses. And one highlight is that I helped devise a bunch of questions that encourage students to think about ethical deployment of AI systems for the Introduction to Machine Learning course at MIT. I've been involved with a lot of undergraduate mentoring through the UChicago Math RU program and outside of that. So I've worked with students to help them learn advanced concepts in optimization and machine learning, and also work on experiments and theoretical problems. And later in the talk, I will talk a little bit about one of the projects I've worked on recently with an undergraduate student that we've submitted to a conference and also presented at a workshop a couple of weeks ago. I like putting together self-contained courses about various topics. So recently I taught a 3-day seminar on information theory at the Toyota Technological Institute in Japan, which is our sister institution. And like I said, I like getting people broadly excited about math and computer science. So one thing I did toward this was I helped run a 10-week Girls Who Code program at a local library near TTIC. So I worked with 3 other graduate students, whom you can see here in the front row, to put together a bunch of materials, teaching students ranging from age 5 to 13, various concepts in computer science. And then in the second half of that program, they put together their own projects and they showed them off at the showcase that we held. So in addition to all of this, I have served on a number of committees and as a student body representative within TTIC, because I think in addition to all of these ways in which we get people more excited about math and computer science, it's really important to have institution level sort of policy and protection for making our environments more inclusive. And so with that, I'll jump back into the research part of the talk. And so I will focus today mainly on these 2 projects, but I'll also sketch some ideas, and this is all sort of within this realm of decision making. The kinds of decisions I'm interested in are ones that require some sort of investment or allocation of effort. So a company might be deciding should they develop technology A or technology B. Or as a student, I might be deciding, should I go get a PhD or should I go get a job? Or maybe we're starting a business and we want to know how long we should keep trying before we should sort of cut our losses and do something else. And the things about this that I'm interested in are, first, how do people make these decisions? And second, how are their decisions affected by those around them? So I mentioned that I'm a theorist. Well, why study these problems with theory at all? The first thing that theory gives us is a way to characterize the realms of possibility pretty formally. So we can say, under these conditions, these results hold. And are those conditions necessary or sufficient? And we can reason very precisely about those things. The second thing is that we can come up with algorithms that help us achieve our desired outcomes. And so we have a very strong way of thinking about procedures as algorithms. And finally, if we can specify our algorithmic or AI systems in a somewhat formal way, we can wrap them sort of natively into our theoretical models. So I'll tell you a little bit more about how I'm thinking about decision-making. So I sort of broke it up into sequential and social decision-making. When I say sequential decision-making, I'm thinking about one individual making a sequence of decisions or taking a sequence of actions and receiving a set of rewards. And so subsequent actions might be dependent on the rewards that they've gotten so far. When I talk about social decision-making, I'm thinking of a collection of individuals that have some relationships with each other who are each taking some action or decision. And I'm really interested in the interplay between these two perspectives. So when I take the sequential decision-making perspective, often we can get tight theoretical characterizations, which then give us a sense of what the best thing we could hope to achieve is in the general social case. And when we look at these complex social phenomena that arise when people are making decisions based on each other, we get new models that we can then hope to characterize theoretically. So in each of these, we have a setting, an algorithm, and an outcome. So we have some sort of setting that the people making the decision are interacting with, some algorithm by which they're making their decisions, and the outcomes associated with that. In the sequential decision-making perspective, I'm going to think about fixing the setting and the outcome and coming up with algorithms that achieve the desired outcome. And when I talk about the improving multi-arm bandits problem, that's the perspective I'll be taking. And on the other hand, when I talk about social decision-making, I'm going to think about fixing the algorithm and thinking about the relationship between the setting and the outcome. So how can I change the setting to get desired outcomes? Yeah.
Can I ask you about your high-level goal?
Sure.
You want to understand how people make decisions as an anthropological project to know how people work? Or do you want to come up with algorithms that emulate how people do it? Like, why don't you come up with algorithms that do better than whatever people do?
Yeah, so it's more of the latter and what you and the third thing you said. So okay. On the more like algorithmic side, I'm trying to come up with optimal algorithms. And then on the more like kind of analysis side, I'm thinking about algorithms that people use in practice to make decisions and trying to see how what kinds of outcomes those lead to and how we can sort of adjust the situation such that those algorithms can still get you good outcomes.
Thanks.
Thank you. Yeah, and so when I talk about the pessimism traps work, I will take this perspective. Okay, so in the rest of the talk, I'll start by talking about this improving multi-arm bandits problem, and I'll take both a worst case and a beyond worst case data-driven perspective on that. Second, I'll go to the social decision-making perspective and tell you about pessimism traps. So stay tuned. That's kind of an unusual phrase. And the third thing I'll do is sketch some future directions that I'm excited about. Okay, so with that, let me jump into the improving multi-arm bandits portion of the talk. This is joint work with Avram, my advisor, Martin, who's an undergraduate student at the University of Chicago, and I've really had the pleasure and privilege of mentoring him alongside Dravi, who's a postdoc at the Ideal Institute. And this part of the talk is based on these two papers. The first one was in Alt this year, and the second one is in submission, and we presented a preliminary version in the workshop 2 weeks ago at NeurIPS. So before we jump into the research problem that we worked on, what is a bandit? So the name comes from these slot machines, gambling sort of situation where you have these machines that you pull the lever and you get some sort of money out. And so the rewards or the money that you're getting, we can think of it as drawn from some distribution. So you get some money, but the next time you might not get the same amount. And we're going to want to quickly identify which arm gives you better reward so that you can just spend the rest of the time pulling that reward. And so this formalism dates back to 1933. So people have been studying bandits for almost 100 years now. In this paper, William Thompson roughly wants to understand if you have two different coins. So here I have a penny and a krona. I want to distinguish which of them has the higher probability of coming up heads based on two or a very small number of flips. So when I think about bandit feedback, what I mean is that we're only receiving the utility of the action that we take. So we don't get any other understanding of our setting. We just know, all right, I took this action, I'm getting this reward. And that's the reward R of A. And so I might take a sequence of actions, action 1, and then I get some reward R of A1, action 2, and so on, where these actions can be dependent on the rewards that you receive in the previous time steps. So concretely, if we're flipping coins, maybe I flip the penny first, I get a heads, I flip it again, I get another heads, I flip it a third time, I get a tails, and then I decide maybe I should be exploring the krona, I switch to the krona, I get a tails, and so on. And again, we want to use that sequence of information to understand whether the probability of coming up heads is higher for the penny or for the krona. I'll give one more quick example. So suppose I'm leaving home and coming to school every day. And I have three options. I can either take the subway, I can drive, or I can walk. And I really care about getting my 10,000 steps every day. I count on my watch how many steps I've gotten. So that's going to be my reward function. Okay. Monday, I walk from school to work and I get 1,000 steps. Great. Tuesday, I do that again. I get 1,200 steps. There was some snow on the ground and I had to kind of walk around it. And so I took a little bit more time. Wednesday, I decide to take the MTA. I have to walk to the station. I have to walk from the station. So I still get 600 steps, but not as many. Thursday, I decide to walk. And that day, it's super smooth. It just takes 800 steps. Friday, I drive, but my parking spot is really far away. And so I actually end up needing to have to walk 900 steps. And so what's happened here is that for each of the arms or actions or the ways in which I can get to work, I get IID rewards. I get independent, identically distributed rewards for that particular arm. So the feedback is that we saw the reward for the action that we took, and the reward structure was that each arm had some distribution according to which that reward was coming from. But in my research problem, I'm going to be interested in a situation where the reward structure is increasing for each arm. And that's going to help us model situations like this. Which research direction has the best payoff? I'm working on a number of different things, and I can see that, I'm getting closer to having results, but one of them is, some of them are going to have higher payoffs in the end than others. Or maybe a company is developing a number of different energy technologies, and they want to decide which ones to invest in and which ones to stop development on. Or maybe you're training a number of different machine learning algorithms, and you have some fixed compute budget. So you want to figure out as quickly as possible which of them is going to be the best without training all of them to convergence. And so we can instantiate this problem formally as the improving multi-arm bandits problem, and we follow the specification in this work. Here we have k different bandit arms, and each arm has associated with it a reward function that increases the more you pull that arm. So each time I interact with the arm or I pull the arm, I receive some reward that's a function of how many times it's already been pulled. Our goal will be to maximize the total reward at time horizon, capital T. We can also handle the maximum reward ever received, but I'm not going to talk about that in the talk. We have the idea. I'm happy to sketch the ideas later offline, but today I'll just focus on the cumulative reward. And we're going to measure this by competitive ratio. So that's the amount of reward you get from the optimal strategy divided by the expected reward of the algorithm. The expected reward of the algorithm. Yes.
So in which sense is it increasing? Is it just the expected, or every draw would be higher than the previous, or what?
So the expectation for alg is going to be over the randomness in the algorithm. For the purpose of the talk, think about the rewards as deterministic. We do show that you can handle like additive noise, but
No, but I mean, you said that the distribution goes up the more times I pull the arm, right?
Right. So think of that as like deterministic. Like just the
Okay.
value is just going up, and it's like
Got it.
you get exactly the value of the
Got it.
function.
Thanks.
Yeah. So if you've heard about bandits before, maybe you're wondering why I'm not studying regret. And the answer is that there are some basic instances where you cannot get non-trivial regret. And so prior work started off studying competitive ratio for this problem and showed order K upper and lower bounds for deterministic algorithms. And there's another line of prior work that does study policy regret, but makes much stronger assumptions to do so. So in terms of assumptions, we're just going to make this one, and that's that our functions follow the diminishing returns property. So this assumption is basically saying that the difference between two consecutive pulls decreases as time goes on. So this is basically concavity. And here are some examples of functions that don't and do satisfy this property. So in the rest of the section, I'll start by giving a lower bound on the competitive ratio, and I'll do this by showing you an instance that all algorithms have to get bad reward on. And then I'll match that with an upper bound. I'll show that there's an algorithm that can actually get you that competitive ratio if it has a crucial piece of information. And it turns out you can actually estimate that piece of information, and you lose only this logarithmic factor in the competitive ratio. I'm not going to go into that in the talk, but I'm happy to chat about it offline. And then I'll talk about learning algorithms from data for this problem. Okay, so let me jump into the lower bound. The instance is as follows. We have one copy of the blue arm that increases for all time, and we randomly assign which arm gets that function. And then we have k-1 copies of this orange arm that increases for the first t over square root k time steps and then flattens out. So the optimal strategy is going to just be to play the blue arm. We're going to get at least t over 2 reward by doing so. And now any algorithm cannot get more than 3 times opt over square root k reward. And the way to see this is that if an algorithm plays an arm for less than t over square root k number of pulls, it won't know whether it's on a good arm or a bad arm. And so it has to play for at least t over square root k pulls before it can distinguish which arm, whether it's a good arm or a bad arm. So it really only gets about square root k chances to find the optimal arm. If it finds the optimal arm, it gets the optimal reward. Fine, we're happy. And if not, it gets the reward of the orange arm, t over square root k. And so you can combine those to get this upper bound on the value of the algorithm's reward. And now we've taken a deterministic algorithm and a randomized instance. We can apply Yau's principle to get a lower bound for a randomized algorithm on deterministic instances. Okay, so now let's see how we can match this omega square root k lower bound with an upper bound. So let's start by assuming we know the maximum value of the best arm, f star of capital T. Like I said, we can estimate this from playing the instance, but I'm not going to go into that. I just want to give you an idea for the structure of the optimal strategy. And the strategy is really simple. We're just going to choose a random arm and keep playing it until we can no longer hope to get f star of capital T reward eventually. So what does this look like? Suppose I have this blue bandit arm and I project it forward with this black line. And the question is whether or not that line intersects f star of capital T, which is this red line up here. So I keep pulling the arm, I keep projecting forward, it keeps intersecting before time capital T, which is 100 in this case. And as I keep doing that, at some point, it no longer intersects. And what I want to understand is how much reward have I accrued when I play an arm for TI time steps. Okay, so when I played the arm for TI time steps, there was some final point at which it still was intersecting this. And we're interested in computing the area of this triangle as a lower bound of the total area of the total reward accrued from the bandit arm. So we know that this is TI minus 1, and we know the values of these parameters, and so we can compute the height of this triangle, which then allows us to compute the area of the triangle, which we can rewrite until we write it in terms of opt, the total amount of reward the optimal strategy achieves. And so now we need to fold this into the analysis of the broader algorithm. To do that, let's take a look at the pseudocode here. So the algorithm chooses an arm randomly and then keeps pulling it until the condition isn't met, at which point it discards it and goes back and pulls a new one. And this repeat block happens each time with one fewer arm and TI fewer time steps. So as a result, I can write this recursive equation, V of T prime K prime, which corresponds to the expected reward of playing the algorithm with T prime time steps and K prime arms. So let's write out this recurrence. V of T prime K prime is at least, well, with probability 1 over K prime, we find the optimal arm, we receive all of its reward, things are good. And with probability 1 minus 1 over K prime, that doesn't happen, something else happens. What happens? Well, we play some arm for little t plus 1 time steps, and we get this reward based on the previous lemma. And then we recurse with little t less time and 1 fewer arm. There's a problem here, which is that we don't know which arm we picked, right? So if we knew which arm I we picked, then we would just use the TI that's associated with that arm, but we don't know that. And so we're going to take the worst case over values of little t, and this still gives us a valid lower bound for the amount of reward accrued by the algorithm. And so you can solve this recurrence using induction, and that gives us an upper bound for the competitive ratio of order of square root k. So as I mentioned, in practice, we probably don't have access to f star of capital T. No problem, we can estimate it by exploring for a little bit of time. And it turns out that, like I mentioned, all you lose is this logarithmic factor when you do that exploration process. So the conclusion of this part is that there's a strategy that helps you solve this problem that involves trying everything for a little bit, using that to make a good guess about what's achievable. So that's that f star of capital T. And from there, only work on the things that will help you get there. And of course, the theory conclusion of the talk is that the competitive ratio for this problem lies within omega square root k and order square root k log k. Okay, so what have we accomplished here? Well, we didn't make a lot of assumptions, and we got nearly tight upper and lower bounds. And in fact, that tells us that, if you have these really strong lower bounds, then you kind of can't do better unless you make more assumptions. But on the flip side, that lower bound instance was a little bit pathological. You don't really expect things to kind of increase and then suddenly flatten, or to be kind of linear as like a minimal example of concavity. And in practice, we might expect to see more structure. So if we're actually deploying this in a hyperparameter tuning case, or like in a case where we're deciding which technology to develop, we might see more structure. So what can we do about that? Well, we could make strong assumptions. That's one thing that we could do. But we don't always know that assumptions hold in practice. And in fact, even verifying whether or not those assumptions hold might not work in the context of needing to verify them and then run this optimization problem. Of course, we're in the machine learning age, so can we just learn which algorithm to use? And so we answered this question in the affirmative in this work that is currently under submission, and we presented at a workshop a couple weeks ago. And we do this by developing 2 families of algorithms. So each of these families of algorithms is a parameterized family, which means that each algorithm in the family has some value of the parameter associated with it. So for some value of the algorithm or the parameter, so in particular alpha equals 1, you recover the worst case optimal algorithms. So the algorithms that in the previous part of the talk we saw are worst case optimal. And as you change the value of that parameter alpha, you get algorithms that are better for instances that meet stronger assumptions. And so in this work, we show we bound the statistical complexity of learning the best algorithm from each of these families. And I once again just want to highlight that this work was done in collaboration with an undergrad, and it was like a really fantastic experience getting to mentor him and work with him, just think through ideas and that kind of thing. Okay, so conclusions for this part, well, we have that the competitive ratio for this problem is bounded between square root k and square root k log k. And we know that we can learn something in the statistical sense from this family, which gives us on average guarantees over the distribution. And so we can get kind of the sharper than worst case guarantee by learning from offline data. So I know I just sketched the ideas in that second part very briefly. I'm happy to chat more about them offline. Yeah.
Your assumption, it seemed like this concavity assumption, it seemed your optimal algorithm kind of relied on that being true for every time step.
Yes.
So just like immediately break if it's like wrong a finite number of times or something.
Yeah, that's a good question. So we show in the paper that you can get away with things being only like approximately concave in some sense. And in particular, the sense in which we show it is that you have a band of like a multiplicative band of 1 plus minus epsilon around the value of the function.
Okay.
In which it has to lie, and then you can still solve it. So maybe the mild caveat there is that like the competitive ratio then depends on epsilon, but
Can you do like iterative doubling or something again
you
to
might
guess
be able
epsilon?
to estimate it or something. Yeah.
Thank you.
Okay. So far we took this kind of sequential decision-making perspective where we fixed the setting, fixed the outcome, we wanted maximum reward, and came up with algorithms for that and optimal algorithms or near optimal algorithms for that. And now I want to switch into this second perspective that I've been talking about, where I sort of fix the algorithm by which individuals are learning or making their decisions, and I want to study the relationship between the settings and the outcomes. So I'll talk about the Pessimism Traps and Algorithmic Interventions project, and this appeared in Fork this past year. This is joint work with Avram, my advisor, Emily, who's a professor at Carnegie Mellon, and Alex, who's a professor at Emory. Alex is also a philosopher, so this is kind of a very interdisciplinary collaboration. And that's something that I really want to highlight about this project that I really enjoyed, and I'm excited to kind of keep pushing on in my future work. We picked up this paper, Resisting Pessimism Traps, The Limits of Believing in Oneself by Jennifer Morton. It was published in Philosophy and Phenomenological Research. And we sort of engaged very carefully with it, read it closely, and tried to understand kind of the core ideas of her argument to build our paper, which is a quantitative model for her qualitative description. And through this process, there was sort of a lot of back and forth between these two papers where, I'd come up with some idea, I'd go back to this paper, read it carefully, see if it's consistent with her description of the problem. And so it was a really fun sort of way to bridge two otherwise somewhat unrelated literatures. And like I said, I'm really excited to kind of keep pushing on this sort of research in the future. So what is a pessimism trap? Well, Jennifer Morton, in that paper I just showed you, writes that a pessimism trap captures how negative beliefs about one's likelihood of success can play a role in agents pursuing less risky, modest ends instead of ambitious ones, thereby further entrenching the negative evidence that the agent herself and other agents in a similar position face. And she highlights that poverty, prejudice, and discrimination can play a role in the formation of these pessimism traps. So what's an example? She talks about how students in high poverty schools might decide not to go to college because they don't see other students from their school going to college. But by not successfully pursuing this course of action, she's not only failing to provide countervailing evidence that people like her can succeed in that pursuit, but she has reinforced the evidential basis for the next student who will reach a similarly pessimistic conclusion. So really, this pessimism trap is about the evidence available to people making those decisions and how the decisions we make sort of add back into that evidence. Okay, so our questions were, first of all, can we model this quantitatively? And second of all, can we then take that quantitative model and come up with some sort of sustainable intervention that shifts communities into optimism? So for this portion of the talk, I'll start by providing the formal model. I'll talk about a single community setting so that we can understand what the structure of the intervention is, and then I'll generalize it to a multi-community case. Okay, so for the formal model, we start by looking at the theoretical economics literature, so more interdisciplinary work here, and we find this information cascade model, which is a decision-making model in which individuals have private signals, SI, and they take public actions, HI. When the next agent comes along, they have their own private signal, SI plus 1, and they take an action, HI plus 1, that's a function of their private signal and the public actions of everyone before them. And this continues. In our model, agents are either in world A, in which case the reward for action A is 1, and the signal is aligned with action A with probability P bigger than 1/2, or in world B, where the opposite is true, where action B is better, and so the reward for it is higher, and the signal is aligned with B with probability P bigger than 1/2. For the first part of this part of the talk, I'm going to assume that this is the actual state of the world. The agent, of course, is not going to know it, but the government is. And before you get mad at me for making what is a very strong assumption, I want us to think about this more as like a condition that helps us understand the structure of the intervention, and we will completely get rid of this in the second part of the talk. Okay, so agents are going to choose between action A and action B, and they're going to do so by with the goal of maximizing their expected reward. They're perfect Bayesians, and so they're going to compute their posterior probability that they're in world A given their signal and the history of actions before them. They'll start with a uniform prior between worlds, and they'll break ties according to their signal. So let's look at an example. Suppose agent 1 comes along, and their signal is B. They compute the posterior probability that they're in world A given that their signal is B, and that's going to be 1 minus P, which is less than 1/2. And so they take action B. The second agent comes along, suppose their signal is also B. Well, then their posterior probability that they're in world A, given their signal B and the previous action B, is still less than 1/2, and they also take action B. And now, when the third agent comes along, even if their signal is A, their posterior probability of being in world A is less than 1/2. And so they also take action B. And so this group has already sort of fallen into a pessimism trap. And you can see how it develops sort of quickly and arbitrarily. And also that, it's not that it happens every single time, but it sort of happens with good enough probability that it could be concerning. So we're going to think about subsidies to get us out of this. What do I mean when I say subsidy? Well, I have a government or some sort of centralized institution providing money for taking some action. And so here, we're really changing the reward structure of the setting in order to try to induce a better outcome, because we are assuming that the agent's actions are sort of fixed in this Bayesian way. Okay, so what's kind of the most naive subsidy we could do? Well, let's just give agent 3 a big pile of money to take action A. And agent 3 is happy. They are going to just take action A as a result of that subsidy. But the problem is now when the government stops providing the subsidy eventually, an agent that comes along is going to be indifferent to the choice of this agent. They're not going to be receiving money to take this action, and so they have no incentive to take it, and they'll fall right back into the pessimism trap. So the design of our subsidy is going to try to overcome this by introducing more information into the system. And so the way we do this is that we're going to incentivize taking action A by just enough that the agent only does it if it's already aligned with their signal. So what does that look like? Well, we want the expected reward of taking action A when their signal is A to be better than the expected reward of taking action B when their signal is A. That's fine. That makes a lot of sense. But we also want the expected reward of taking action A when their signal is B to be lower than the expected reward of taking action B when their signal is B. So little r sub t here is the subsidy, and we want it to kind of have both this lower bound and this upper bound. And it turns out you can solve for the value of this, and it's a function of the number of A actions minus the number of B actions. So this has this really nice self-tapering property. So when you get to a point where you have a lot more A actions than B actions, the value of the subsidy is actually really small, and you can kind of do away with it because there is enough information in the system at that point. How do we analyze this? Well, let's go back to the main idea where we sort of had this signal revealing property of our subsidy. And the signals are just Bernoulli random variables, right? So they are A with probability P bigger than a half, B with probability P less than a half. And so we can actually map this onto a random walk with bias P. And from there, we can analyze things like the budget for the subsidy, how long it needs to be in place to get people out of pessimism traps with high probability and things like this. So the first big insight then in this work is that as a function of subsidy size, if the subsidy is too small, we're stuck in the pessimism traps. If the subsidy is too large, we're actually indifferent. And so it's not really useful to do that. But there's this sort of middle region that's really kind of where progress is happening. And so this non-monotonicity of the subsidy is somewhat unusual and kind of interesting as a result.
Sorry, when you say indifferent, you mean we're indifferent to our signal?
We're indifferent to the actions of people that were subsidized. So yeah, so not making any progress toward yeah. Okay, so let's extend this to the multi-community case. So we started off with just having one group that had one correct choice. And now we're going to think of having k different groups, each of which live in a different sort of world. So for some of them, action A is better. For some of them, action B is better. And the agents are going to mostly behave the way they did before, but they're going to make their decisions based on the people only in their group. So only the people in their group are sort of relevant to them to make decisions. The government is still going to provide the subsidy, but they're not going to know which agent is a part of which group, and they're not even going to know which choice is correct for which group. So I told you I was going to get rid of that really strong assumption that A was the correct action for everyone, and I have. They're not even going to know which choice is correct. So an agent comes up to them, they have to do something, and hope that in the end, everyone will be optimistic. So
their goal, the government's goal, is to get people to do what their signal says, ignoring what their community does. Is that a correct understanding?
In the short term, yes. So in the short term, their goal is to get people to reveal their signals. And in the long term, the hope is that with enough revealed signals, you have enough information for people to be taking the better action for that group. But the thing is, like, the better action is different group to group. Did you have a question as well? Okay. Sounds good. Okay, and so the way we're going to do this is with randomness. So we're going to define a random process that ensures positive probability that that subsidy is in the progress region for each group. So if you remember from the couple slides ago, there was this one region where you are actually making progress toward breaking out. And as long as there's positive probability that the subsidy is in that region, we're actually making progress. And so our second main insight is that randomness in the subsidy encourages people to figure out and follow what's good for them without sort of governmental paternalism. So here we fixed the setting, we fixed the algorithm, so people are Bayesians, and we investigated the outcome, and we got these pessimism traps. And we weren't happy with that. And so we changed the setting, or we tweaked the setting by introducing this subsidy to get better outcomes. So I want to quickly sketch some ideas in a similar work that we had called A Theoretical Model for Grit in Pursuing Ambitious Ends. This will appear in AAAI in a month in 2026, and it will be presented as an oral. So here we took Okay, so I should say, here we're interested in modeling people's behavior when they have more or less grit. So if they're more resilient, more optimistic, what does that look like? And this is again in conversation with another paper of Jennifer Morton's and with her colleague Sarah Paul. So to study this, we came up with a very particular improving multi-arm bandits instance. And this one sort of is meant to model what it looks like when you're deciding between an option that kind of gives you a weekly or biweekly salary versus something that really doesn't pay you at first, but eventually starts to pay off really well. So maybe college or grad school or things like that. So we kind of fixed the family of algorithms that agents in this problem are going to be using, and their goal will be to maximize their competitive ratio. And we studied the outcomes. And in particular, we found that there were settings where more grit actually led to less reward, which corresponded to some literature in the social sciences and sociology in particular that talks about the effort paradox, where people that work harder sometimes end up with worse outcomes. And we also studied how tweaking the setting by giving people financial incentives changes their outcomes. So that's, again, a very high-level sketch of the ideas in that work, and I'm happy to chat more about it offline.
You say more grit led to less reward. How do you define grit in this context?
Yeah, so here we were looking at so the slope of this payoff is not known, and individuals have guesses for that slope, which corresponds with their level of grit. So if it's sort of like optimism in that sense, where if they think that the arm is going to pay off better, then they'll kind of stick on it for longer. Whereas if they're less confident that it's going to pay off, they'll sort of switch to the stable option faster.
Okay, thanks.
All right. So with that, I will tell you a little bit about some future directions that I'm excited about. So the first is just extensions for the improving multi-arm bandits framework. So right now we sort of use this hyperparameter transfer idea to learn good algorithms. And so I didn't really go into the weeds with what this hyperparameter transfer idea is, but it comes from a paper that was published earlier this year. But one interesting question is, like, what other instance structure can we adapt to? And can we use even more general adaptive approaches? Could we warm start? So right now we're choosing bandit arms randomly with a uniform distribution over the arms, but maybe certain arms have a higher probability of being good arms than other ones, and we want to learn a better distribution. Could we do something fully online? Here we had some offline data, learned something, deployed it on the new instance, but maybe we can just learn online as well. Okay, so the second direction I'm interested in kind of extends the modeling ideas in the pessimism traps work. So that was one social learning model where we looked at interventions. And I'm interested in ones that show polarization. And I think it would be really interesting to try to characterize what necessary and sufficient conditions are in some of these social learning models. So there are people that are kind of looking at some of these polarization, some of these social learning models that show polarization. And really what I'm most interested in is how can we intervene to stop people from getting so polarized? And really the goal there is to maintain and share a diverse set of opinions, which then also has connections to things like AI alignment. So far, I've kind of talked about learning from your own experience interacting with an environment in this improving multi-arm bandits problem. And I've talked about learning from others around you. And I'm really interested in combining these. So taking the sequential decision-making perspective, it would be interesting to think about a model where you take some action and you get bandit feedback. So you get to see what reward for the action that you took. But then you also see actions of people around you and you want to help use that to inform your future actions, but you don't see their rewards. And then in the social decision-making context, that sort of modeling is interesting because tying together some of the ideas from this pessimism traps work and the grit work, we're interested in understanding what role individuals who are gritty have in their community more broadly. So do they play roles as role models? Do they convince people to, take on certain things, or do they convince people away from going towards certain paths. That's something that I think people are really interested in the social sciences, and it would be interesting to kind of unify some of these modeling ideas and think about more. So like I mentioned, we have some work in looking at grit on its own, but it would be really interesting to incorporate this into the social perspective as well. So more broadly, I want to keep pushing on this interplay between sequential and social decision making. And one thing I think would be really interesting to study from this perspective is our interactions with AI systems. And so there's been a lot of work recently starting to ask this question of, are we losing our skills because we're so dependent on AI systems? But on the other hand, we're also really benefiting from the kind of access to information and access to sort of everything that comes with these AI systems. And so I think it could be really interesting to use this perspective of sequential and social decision-making to think about the sequence of decisions individuals make when they're interacting with AI systems. But then also, what do those social interactions, so to speak, look like when they're interacting with non-human agents? And one use case where I'm really interested in studying this is in education. So how are students using AI systems to learn? How can we sort of make better kind of AI system human interaction protocols that then help students learn and not just become reliant on these AI systems? So thanks so much for listening to my talk, and I'm happy to answer more questions.
All right, we can take questions in the room. We can also take questions in the Zoom. And if you would like to ask a question on the Zoom, you can either raise your hand and then we can have you unmute and ask your question, or you can type it into the chat and we can read it for you. And those in the room, questions?
So I was wondering about the sort of social learning and the work you did around the subsidies. I was thinking, for many of the examples that you mentioned about should I go to college, should I, do a PhD, I don't really see the outcomes of everyone in my group, quote unquote, right? Maybe, there's some people of my group that I hear about or I see in the news, or like someone, introduces me to someone else in my group. So I was wondering if the same effect that you get with the subsidies, you can get by changing which of the prior group members that person sees or has access to. Like, is that something that I think what you said about role models at the end can be similar to that, right?
Yeah, that's a great question. I actually think people have studied this in these like information cascade models, how you can sort of restrict access to information to try to get people to not cascade, kind of go into one of the directions or the other. One of the things that we found sort of attractive about this is that we gave people we just let people do whatever they were doing already, and then we sort of shifted things around. But I think, yeah, like you say, what you're describing is another way to sort of change the outcomes as well. And yeah, I think it's interesting to think about creating role model, making an example of someone I think has a negative connotation, and then making someone a role model has a positive connotation. So I think that's also interesting. I think there are questions of like who's deciding to make this person like the role model? Like if it's my job and I have some sort of ill intent, like could I then make role models of the wrong people? And I think that's something that I would be concerned about.
But you could also give subsidies to the wrong people with the wrong intentions, no? Like somehow you brought up the adversary suddenly, but doesn't it apply to your model as well?
Right. So I think
I think what Sylvia asked is similar to advertising, which indeed brings a negative reaction in me because I don't trust them.
Yeah.
But why should I trust them in your work?
So that's a good point. So in the first part where we only had a single group, we explicitly assumed that the agents don't trust the government. Because if they did, then they would just see which action the government is subsidizing and take that action, whether or not they get the subsidy. So we do assume that we don't trust the government. And then in the second part, the trust for government sort of that goes away because the government is using this random process. And so you don't need to sort of trust or not trust them. You just sort of either get the money or you don't. So we did try to kind of address that in sort of modeling.
I think my question maybe builds on Sylvia's. So in the future work example, one of the future work examples, you talked about saying that one agent learns everyone else's actions, but only its own reward. And I feel like more realistically, really both of those are partial. Even your own reward can be partial information, but definitely you maybe have some ideas about actions that other people take, and you may have some idea about the rewards that they did or didn't get. And so I wonder if that's something that's been studied sort of in this other literature that you're looking at for examples of modeling, or if that would be a really sort of new area to look at and understand.
I think so, yeah. I'm not aware of models that sort of do what you're saying, where both you have partial information about your own reward and also have some sort of partial information about other reward. I think it would be a really interesting model to study, and this was more meant as like kind of a simple first cut, like you have this from one person, you don't have this from another person.
Yes. And Augustine online has a question. Go ahead.
Thank Kavya for the wonderful talk. I'm so excited we meet later and I can ask many questions. I had one overall question, which is in a way, sometimes you assume that the reward is diminishing return. Sometimes you do the exact opposite to understand grids. So this looks like when did the shift went from diminishing return to the other one? Have you since you've studied also with other social science, you see where diminishing return makes more sense? It seems important, and I was just wondering if you can elaborate on when these assumptions are best used.
Yeah, that's a really, really good question. So yeah, we use the diminishing returns assumption in like the theoretical development of the for these like near optimal algorithms for the improving multi-arm bandits problem. So I think that I view that as like a much broader setting where you can kind of think about things like technology development or like hyperparameter tuning or, you know, algorithm selection or things like that, where you do have a, you know, maybe there are like I think there are like empirical reasons to sort of think about this diminishing returns property. And then I think in this context of ambition and outcomes related to that, it is often the case that, you know, you don't sort of get to see a lot of your reward early on. And so I think that I'd like to think more about where those assumptions do and don't hold, and if there's some sort of like more systematic way in which we can think about like, yeah, settings where, you know, you do have diminishing returns versus ones where, you know, you're really kind of doomed. You have to kind of suffer for a long time before you see any reward.
I mean, yeah, it might lead to different type of exploration. I mean, many exploration at the very beginning when it's really terra incognita, it looks like diminishing return is a little limiting. It's more for mature sort of, you know, technologies that we perfect. That's why it's an interesting difference. I also was curious, how do you make this estimation? Because it doesn't seem very easy to estimate this with a logarithmic number of trial. You can estimate the best you can hope for. So is it because you use diminishing return a lot? Or
Exactly. Yeah. It is pretty significantly dependent on the diminishing returns property. So the procedure is basically just that you pull each arm to t over 2k times, and then you use that to come up with some band within which the parameter has to lie. And that band has the sort of like ratio size order k. And so then you can, I don't have that last slide in there. But basically then you can break that band up into doubling subintervals and then just choose one at random. And so you get log k or order log k like subintervals, and you have a 1 in order log k probability of picking the good one.
Okay, yeah, that makes sense. I had more questions, but I don't want to overwhelm. There might be others in the room. So,
any other questions for now then? I will let you all know that Kavya will be having a cookie break at 3:30 in Milstein 5 14, which is the open space down on the 5th floor on this side of the room. Anyone is welcome to join for that if you have the ability to get onto our campus, which means you're a Barnard or a Columbia affiliate. So feel free to join for more conversation and some cookies, 330 Milstein 514. And seeing no further questions, let's thank Kavya again.